In chemistry, we often have to solve numeric problems, and one of the things that you probably have noticed about yourself and about people like you is that most people are not very good at this. And there's a reason for this. It's not because people are stupid. The real reason is that people don't have the tools that they need to solve quantitative problems, numeric problems. So what I want to do is show you a couple of powerful methods that are really useful in solving all kinds of quantitative problems. This will be real helpful in chemistry class, but it will be also helpful in other classes that you'll take that are numerical, and it'll also be very valuable in real life. Because in real life, nobody ever has a job or solves any of their personal problems by just answering questions like are in a textbook. That isn't what real life is like. Real life is all story problems. It's all these quantitative, difficult problems that you have to solve, and it's great to be able to have a tool that makes that approachable. The big problem is people don't know how to get started, and this method I'm going to teach you now, called the APE method, is just a way to get started. You're smart enough once you get started to know how to solve most problems, but most people don't have a good way to get started. So here we go with the APE method. Each of the letters in APE stands for a different part of this method. I just kind of made this up based on how I thought about solving problems. I used to be an engineer and worked in the science and technology fields for a long time, and I realized that I was pretty good at solving these problems. So I analyzed my own methodology, and I came up with these 4 steps that I almost always use when I solve quantitative problems. The A in the APE method stands for analyze, and that's the first step. The first thing you want to do is approach every problem asking yourself 2 questions. What do I know? So what data is given to me? And what do I need to find? So you're basically analyzing this to figure out what data do I have available and what really is the heart of the question. And most people don't ever get to that step, and so they kind of fail at story problems. Let's learn by example by analyzing this problem. I'm going to read through this carefully and pick out all the things that I know. And here's what's really helpful. Instead of just like highlighting them or underlining them or something like that, writing down the symbols that characterize them, because ultimately you're probably going to want to use some algebraic formula, something that you've learned in chemistry class, if it's a chemistry problem, for example, to figure out the answer to the problem. So it'd be helpful to assign each one a variable name so that you have some way to fit it into an equation that can solve the problem. So this question says 250 milliliters of water. Okay, 250 milliliters, that's a volume, is put on a stove and its temperature goes up from 25 to 100 degrees C. Okay, well that's a change in temperature. I saw that in something earlier. Delta T is change in temperature. How much energy was transferred from the stove to the water? The specific heat of water is, okay, there's direct data right there. Specific heat of water is C, 4.184 joules per gram per degree C, and the density of water is 1 gram per milliliter. So that's D is the symbol that we've used for density. And then the second question that you want to answer when you're analyzing a problem is, what is the question? What are you trying to find? And that's very clear here too if you read carefully. How much energy was transferred from the stove to the water? So energy, that's heat energy, Q. So let's sketch out the things that we've analyzed here. Just make a list. We know volume is 2,500 milliliters. We know that the temperature change is 100 degrees C from 25 degrees C. That's how much it changed, and that's 75.0 degrees C. We know that the specific heat for water is 4.184 joules per gram per degree C. And sometimes a picture helps as well. And so we've got water in here, and we've got a stove here. There's our stove, and we know that the heat is going from the stove into the water. So that might help us visualize what we're really trying to find here. How much energy went into the water? How much came from the stove? Well, it has to be the same amount. And we don't have any data about the stove, so we're not going to worry about it. We're going to worry only about the water. And then the other piece of data that we had was density. Density is 1.00 grams per milliliter. And what do we need to find? Well, that was Q. Q is our question mark. So we've analyzed this problem by sketching out what do we know and what is it that we need to find. The next step in APCE is P for plan. Here's what we're doing here. Again, we're asking questions. The first question might be the only one you have to ask. Is there an equation that links what I know, the stuff that I just analyzed that I know, to what I need to find? So once I've analyzed, now I want to start putting together my need and my know with some equation, some formula, some relationship that I've learned about. Sometimes you can do that in one step. Sometimes you have to ask the second question. Can I get there with more than one equation? So sometimes I'll know something that can give me something I don't know, which I can then use with other things that I know to get the final thing I don't know, the final thing I need to find. So we're back on our little sketch pad here, and let's do the next step. Let's make a plan. So here's the stuff I know. I know V, I know delta T, I know C, and I know D, density. Do I have a relationship that links Q to any of this? Q is what I need to find. And I do. I know this. Specific heat is Q divided by mass times change in temperature. That's an equation. If I have everything I need in there except for Q, well then I can solve this problem. What do I know and what don't I know? I know C. I'm given that in the problem. I know delta T. I figured that out already. Here's what I don't know. I don't know mass. So in this case, I'm going to have to ask that second question. Can I use two equations to get this answer? Do I have an equation that links mass with anything that I know? And in fact, I do. I know that density is equal to mass divided by volume. And I know density, and I know the volume. That's given to me. So I have the two things I need to solve for mass. Once I find mass, I can put it in this equation, and that should allow me to find Q. Now, I like to do my algebra with symbols because it's way, way easier. So I'm going to solve this equation here for Q. If I multiply both sides by mass times delta T, here's what I come up with. Q is equal to specific heat times mass times delta T. And don't forget, if you're uncomfortable with doing algebra, you can use this little device here that we saw in an earlier podcast. Cover up Q and it tells me what to do. C times M times delta T. So I'm going to do some algebra on this thing to find out how to get M from the two terms that I have. And I solve for M by multiplying both sides times V, and density times volume is my mass. So here's my plan. Take my density and volume and get mass. Then I plug my mass in here and I get Q, and I'm done. So now I'm finally to the next step, which is compute. And unfortunately, lots of students think this is the first step. Just pick up your calculator and compute. If you don't have a plan, you're just guessing in many cases unless the problem is extremely simple. So here's what you do when you compute. Plug in the known data and calculate. But when you're solving a scientific problem, there are a couple of things that you want to keep track of. One is you want to make sure your units work. And then the second thing is you want to watch your sig figs. Make sure that when you get done with all your calculations, you don't have more or less precision than you originally started with. So back to our problem here. Our plan was to calculate mass first from density and volume. So I'll start doing that. Mass is equal to density times volume. Well, our density that's given to us is 1.00 grams per milliliter. And I like to use this format to help me keep track of units, of making everything into a fraction. One isn't a fraction, but 1 gram per milliliter can be written as a fraction, and it makes it easier to visualize what's going on with the units. Now I'm going to multiply by 2,500 milliliters. 2,500, and I want to make sure that I put that decimal point there because that affects my significant figures. So now I'm going to first, before I do anything, look at my units. Milliliters cancel because they're top and bottom, and that's going to give me grams. Is that a good unit of mass? Doing a little check here. It is. Grams is mass. So now I'll do my arithmetic. 1 times 2,500 is 2,500, but I've only got 3 significant figures here. So even though I have 4 in 2,500, I've got to round to 3 significant figures. Well, there's no way I can write that without using scientific notation, so it's got to be 2.50 times 10 to the third grams to report the right number of sig figs. Well, I calculated mass not because I needed mass. I calculated mass because I needed to put it in my Q equation. That was the point. So that goes up in there. So what's Q? Q is specific heat. Well, that's 4.184 joules per gram per degree C times mass. Well, my mass, I now know, is 2.50 times 10 to the third grams times the temperature change. Well, earlier I calculated that the temperature change was 75.0 degrees C. Again, the first thing I do is not numbers, it's units to see if I'm on the right track. Degrees C cancel, so do grams, and I have units of joules. Joules is heat energy, and so since my units are right, probably my answer is going to end up being right. Well, now I'm finally ready to calculate, and when I put these numbers into my calculator, I come up with three significant figures, 785,000 joules. The last step is a step that lots of people skip and shouldn't. E stands for evaluate. You want to give yourself a couple of chances to catch mistakes. The first thing you want to do is ask yourself, are the units right? And I've already sort of done that as I went through the problem by making sure that I was keeping track of units as I went along. Are the units right? Well, yeah, I ended up with joules, and joules is heat energy. And then the other thing I want to ask is, does the answer make sense? Sometimes you can answer this easily. Sometimes you can't really answer this at all. If you have a good feel for the range that the answer should be in, this is a good evaluation step. We got 785,000, which seems like a big number, but I don't really have any feel for joules if I'm not a scientist. So what I'm thinking about is trusting my numbers, because I know I set things up right. I know my units came out right, so it probably is right. There are times when this becomes quite obvious. For example, I often have AP students do a lab where they have to analyze how much aspirin is in an aspirin tablet, and sometimes, even though the tablet only weighs about a gram, I'll have people who give me answers that are more than a gram. There can't possibly be more than a gram of aspirin in a tablet that only weighs a gram. So you can ask yourself, in many cases, does the answer make any common sense at all? Try this one. We're going to break this down in steps. I want you to first analyze this, stop the video and analyze it. Write down all the stuff that you know in terms of symbols. And then I'll do it too. So you can check out your analysis. Then we'll make a plan, then we'll compute, and then we'll evaluate it together. So go ahead and analyze this problem now. Okay, here's my analysis. I see a volume, 20 milliliters. I see a Q, 5,000 joules. I see a change in temperature. The temperature increased by 184 degrees C. And I see a specific heat, so that's a C. Now I've got all the things I know in terms of symbols. What do I need to find? Right there it is. What is the density of gold? So D is my question mark. So let's get this on a sketch pad. I know V is 20 milliliters. I know Q is 5,000 with a decimal point, joules. I know that delta T is 184 degrees C. And I know specific heat is 0.129 joules per gram per degree C. The density, that's what I'm trying to find. So there's my analysis. Now, come up with a plan. Okay, here's my plan. I'm thinking about what I need to find, and here's the only equation I know that has density in it. Density is mass divided by volume. And then I stop and think about what I have. I have volume. Mass, I don't. Now, I have to look at the other things that I have in my known from my analysis and see if I have anything that links mass to them. Well, I do. If I think about these three quantities here, mass is related to them by the specific heat equation. So specific heat is Q divided by mass times change in temperature. How can I rearrange that equation? Well, I can do a little algebra, or I can think about this little device, Q mass times C times delta T. And if I want M, cover up M, it tells me that mass is equal to Q divided by C times delta T. So this is the form of this equation that's most useful to me because it tells me how to get mass. Once I find mass, I can plug it in there, and that'll allow me to get density, and density is what I'm ultimately looking for. Okay, I think I'm ready to compute now. So I'll first find mass. Mass is equal to Q, which is 5,000 joules, divided by C, which is 0.129 joules per gram per degree C, times delta T, which is 184 degrees C. Like always, I'm going to check and make sure my units are right first. I have joules on top and bottom. That cancels. In the denominator, I have degrees C top and bottom. That cancels. The only unit that I have here is 1 over grams, but that's just grams. So that's units of mass. Things look pretty good. I'll calculate. I have 3 significant figures in my answer, and it should be 211 grams. Here's why I found that, because I wanted to find the density. So density is mass divided by volume. And my mass, I now know, is 211 grams. And my volume, I have always known, was 20 with a decimal point milliliters. Here are my units. Nothing cancels out. It's grams per milliliter. I should have 2 significant figures in my answer. When I divide 211 by 20, I get 11 to 2 sig figs. So my answer is 11 grams per milliliter. Now the last step is evaluate. I've done my computing, and I have to figure out if my answer is reasonable. Well, one thing is grams per milliliter is a unit of density, so that's good. And I can also apply a little common sense to this. In the last problem, I learned that water was 1 gram per milliliter, and this is heavier than that. This is 11 grams per milliliter. And everybody knows that a piece of gold would sink in water. Almost all metals do. And so, therefore, it's reasonable to think that my answer really should be 11 grams per milliliter. In the next video, I'm going to show you about another really powerful tool called dimensional analysis. And the two of these combined, APE method and dimensional analysis, can solve almost every problem there is, even some quite difficult story problems. So stay tuned for that.